Hello, this is second part of the code changes in MapDB 2. This is sort of low level video for the developers who are interested in MapDB internals. It's not meant to be for users, so if you want to use MapDB without actually knowing on what's going on inside, please don't watch this because it will just leave you a little bit confused. This is sort of very quick and dirty video before we have sort of proper documentation. It's unscripted, so please apologize my mistakes or sort of slow speaking and stuff like that. So yeah, let's start. In the first part of this video we went through the changes in the collections and serializer base, and we started what's the name of that thing, engine hierarchy. So I'll just go back to the engine hierarchy here, and yeah, so in the engine hierarchy we have this, and it produces number of logs, I think, and in MapDB basically we reduce number of logs from 600 to the 16, and it was done by merging various components in this which were various components which had their own locking layer, which were each thread safe on its own under the single locking layer in the store. So basically by making some engines subcomponents of the store, we reduce number of logs by a huge number. I would like to illustrate it on the cache example. The hash table is the cache which is used by default in the MapDB. It's a fixed size, relatively primitive architecture, but in MapDB 1 it was implemented in engine, which engine has like 6 different methods: update, delete, so on. And it also has to be thread safe, so it has number of logs. CC concurrency number is 128, so obviously this is huge, and loads of overhead. And if you look in here, for example, the get method is very complicated, or relatively complicated, I would say. You have to handle the underlying engine because this is wrapper, and you sort of have to synchronize the states, and it's not really that clear. Compare it with MapDB 2. You have a hash table here. This class doesn't have to be thread safe under certain configurations. There is log, but in some configurations you can actually eliminate this log. I'll explain it a bit later. It doesn't implement engine interface but cache interface, which is only has a two relevant method, get and put, which obviously makes it much simpler. Yeah, I'm just got lost a little bit. Hash table, and for example, if you take a look at the put method, obviously this is relevant code, and I would say it's much simpler compared to the previous version. Maybe you wonder, I'm saying that this can be thread unsafe, but it actually has logs. So in MapDB 2 I added something called locking modes. If I go into the store get, in here you can see that the logs are read-write logs, and the get method is capturing the read log, and obviously the update method, which is modifying the data, is using write log. But because the read log can have multiple consumers, the cache on its own has to be thread safe in this configuration. And I did some investigation performance wise, and the read-write log actually has a sort of huge overhead for some cases. It has the read-write log can have multiple consumers and or multiple logs, multiple threads holding the read log, which is sort of unnatural for some CPUs or most CPUs, and it's kind of hard to map it on the many scenarios. So if you compare it with single log, the read-write log is I don't know, about 5 times slower, which is considerable overhead. So sort of battle it, I introduced the locking modes in MapDB too. So the first locking mode, which is on by default, is obviously read-write log. So if you have a multiple readers and no writers, you are practically log free, and the read stops at the moment the writer gets exclusive log and so on. But this is not that great if you have a mostly writers, because the locking has a considerable overhead. So the second locking mode is the read-write single log. I'm not sure how to explain it, but basically I implemented the read-write log, which only has a single log, and the read log is shared with the write log. So you can actually have only single reader, only single writer, which is obviously far from the best ideal situation, because you cannot have multiple readers at the same time. But on the other side, it's much faster to actually log. It's a much smaller overhead, and in some configuration, in some situations, mostly if you have mostly writes, this is actually faster. And third mode is actually you can actually disable the locking. There is sort of fake lock, and in this case, if you have a single threaded application, you actually do not need to use thread safe locking in MapDB at all. You can just disable the locks. I'm not sure I will enable this option anytime soon, because it introduces loads of possibilities for the misconfigurations and sort of false alarms and false reports, but it will eventually be enabled. So anyway, it's nice to have these options for benchmarks and certain usages. Okay, so that's the locking architecture. One important change in MapDB is that the concurrency factor was reduced from 128 to 16. 16 is actually a very low number, and it actually corresponds to about 4 CPUs or maybe even 2 CPUs. So MapDB 2 will not be that much scalable. It should probably scale linearly up to the 4 CPUs or 4 cores. I know what you think. It's probably that it's not that great decision and so on. The problem is that the concurrency factor actually has a huge overhead, because I'm using per segment caches and so on. If I would increase this to 128 again, it will create considerable memory overhead. And from what I found, that the number 16 seems to be like sweet spot, because in reality you don't really have a CPUs with 8 cores or even 30 cores as I do, but 99% of the consumers or users have maybe single core or maybe even 4 CPU cores. So basically I decided to sort of do trade-off and make MapDB scalable linearly up to the 4 CPUs. There are 2 things you should know. I have a prototype which sort of modifies and takes away the shared state. I call it spin memory allocator. Basically I take the allocator, put it in the separate thread, and set thread affinity and so on. It has a considerable overhead on the single or on the small machines, but it scales linearly up to the 30 cores. So that's some pretty nice stuff. I will probably present it a bit later, but it will be in the separate version of MapDB, because it doesn't really go that well with single-threaded architecture. And the second thing you should know, that if you go on Amazon and you buy 30 CPU machine or 32 CPU machine, on Amazon the CPU is not actually, it doesn't actually guarantee that you will get separate cores. It's just measuring performance. So if you, let's say if you buy 8 core machine, you have two options. Either you end up on some sort of Atom, which is not that fast, and it will actually have 8 CPUs, but there is also a huge chance you will end up on the single CPU, which will be very fast. It will be 8 times faster than that Atom or the basic unit of performance. So be careful if you are like renting 32 CPU machines and it doesn't scale to the 32. In reality, the underlying hardware may not have actually that much CPUs as is advertised. The CPU on Amazon and similar services is not the physical CPU, it's just measurement of the performance. How fast is the CPU, or how much CPU you have allocated for your application. Anyway, I think scalability up to 4 cores is good. I still have to be fast enough on the single core, so there's trades-off to be made and so on. And I will release the updated version if somebody will be interested in the higher vertical scalability. I have a 24 CPU machine, and that prototype, the spin allocator, works quite well in there. Okay, so that's the caches, concurrency. Let's move to the internal collections. MapDB 1. Let me get to the nodes. Yeah, okay. MapDB 1 is using collections internally. I end up with collections like this. All the time. Okay, so this is a map which is mapping some sort of ID to offset, blah blah blah, and it has a long key as a key and long as a value. But it creates sort of performance bottleneck, because each map get requires unboxing the value, and it sort of creates it's sort of slow if you are just using hash maps. So in MapDB 1 I introduced, or actually this sort of collection was much earlier. It was JDBM 2 or 3. It's quite old anyway. I sort of overridden I sort of refactored the implementations in some classes, and I introduced long hash map, which is actually map and some generic object here. And this is not typo. The lowercase is actually here correct, because it's using primitive keys, primitive long as a key. So get operations do not require unboxing. Then there are flavors of this. You have a long map interface, long hash map, then you have a concurrent version and LRU version and so on. It's a bit complicated. But the key here is that in MapDB 1 I was using collections which were optimized, which didn't require unboxing. But about a couple of months ago I found callback collections, and I was kind of fascinated because while this long hash map is about 3 times faster than the regular hash map, the callback collections were about 100 times faster than my sort of optimized classes and stuff. Or maybe not 100 times, maybe just 10 times, but it was quite amazing. And it turns out there is sort of thing called like CPU cache, and you have to be CPU cache friendly and so on. And my collections were not really that great, because they were still using internally nodes and stuff. So for each object for each entry you have to allocate the object, and there was reference and there was jump, and there was creating new objects and so on. So it wasn't that performant. So What I did in MapDB 2, I ditched long hash maps, and all those long, basically those 4 classes are gone. Oh, sorry. Yeah. Okay, sorry. It was creating sort of overhead, so I went with Colobog collections and actually integrated them into the code in here, into the MapDB. So there is sorry, there is long map, which is basically using primitive long as key and primitive long as value. The nice thing about this is that it's using only single set for the both key value pairs, and it's very fast with sort of optimized code and no GC at all, or very minimal GC when there is rehash. Then there is second collection, which is long object map. Again, it's not using entries. It's a set, primitive set for the longs, and then there are no entries for the values, but rather object array. Again, very little GC, much faster. And then there is third case where I basically had a map long, and there was composite value, string, something, object, whatever. So basically creating new par and stuff was not very fast, and it was again more garbage collection, more garbage stuff, so more garbage. So I just created long object map, which is basically as a pair of values. I really have to thank the Roman Leventov and Higher Frequency Trading Company, because its Colobog is amazing library. It has like 20 megabytes, so I couldn't really afford to make it a dependency, but I just extracted classes I needed, and it's much faster. So that's good, I guess. Okay, that's our collections. Let's go to the stores. It's something I would like to talk about a lot, but I'll make it short. Basically, the store in MapDB 2 was completely rewritten. One of the major changes is that we have a proper specification, format specification, which was written alongside as the store was developed, so it's actually active or sort of valid, and so it should be quite usable for people who want to study the MapDB and how it's done. There will be some sort of manual, so this will be published as appendix. It's already on my GitHub site, or there is MapDB site project, so you can dig it out if you want. Just search format RST. And another thing in store is that the classes are written in much cleaner way. So you actually have a proper hierarchy. Each object is overriding methods which needs to, and stuff like that. Just to give you an example, there is delete method, and you have a generic implementation, or not, sort of helper implementation, which is taking care of caching and locking and stuff. And then you have a sub implementation, which is actually abstract, and it's already in the proper implementators. This is abstract class, but it doesn't have to take care of locking, so all this code is not duplicated in the subclasses. I think there was like 40% code reduction in the storage, which is quite nice. It makes it more maintainable and much more simpler, and it's also folding much nicer. Another thing in stores is that before we had some sort of problem with corner cases behavior, for example how the null should be handled and what happens if you delete null, and what happens if you delete pre-allocated records and stuff like that. So I sat down and I wrote proper specification for the storage for the engine interface, and I wrote test cases and stuff like that. So basically this sort of behavior is pinned down, which is very nice, because upper layers such as collections can now rely on this behavior, and they don't have to handle corner cases themselves. So again, it's some code reduction and stuff, so that's quite nice, I would say. Okay, let's go to the another thing in the store is the parity. Basically one of the problems I had with MapDB 1 was the where file pointers, for example, if you have a index table and it was pointing to some sort of location in the physical file, and this value will get corrupted, you will get data overridden, and it will be very hard to diagnose that the file pointer is responsible for corruption and stuff. So what happened here is that I'm using parity bits. So each pointer has a basically parity, a small number of bits reserved for the parity. So on each read we can detect if the pointer is not valid by simply comparing the last 3 or last single bit with some sort of value, and if this is broken we just throw an exception. There's obviously some probabilities. For example, if only a single bit is used for parity, the chances of catching up the error is only 50%, but it is still good enough to detect the problems early, because it means it means that the database will fail fast in case of some sort of corruption, and not that many data will get corrupted, and it will be much easier to diagnose what is probable cause of the problem. Okay, let's go to the stores. The store direct hasn't changed much. The only major change is that it's using single file rather than 2 files. The index table was merged into the major store, into the physical file, so that's nice. There is new class between store direct and store write ahead log. Basically this is providing sort of write cache for the store direct, and the idea is that for on the disk space where you have sort of latencies for reading writing, this should provide much faster performance, because some key values and some key components of the store are stored in the cache, and you also have a write cache which is grouping writes into the single flash and so on. That's nicer. That's very nice. There is major change in the store write ahead log. Basically the commits are now done in the two modes. If you have a regular commit, it's the data are flushed into the write ahead log, but the write ahead log itself is not being replayed into the main file yet. Rather than the changes are still kept into the on heap, and every number of commits. Right now I think it's 16 every 16 commits. I'll make this configurable. The those pending logs will get replayed in the main file, will get merged into the main file. Obviously this is quite good for the performance, because you don't have to call the file flush like 3 times on every commit, but only single times, and every 16 commits you do the proper replay. So in this case the commits are much faster. Yeah, there is a number of changes in the format and some small improvements and so on, but I will not really address the changes in the storage yet. It's probably for another video, so I'll just skip to the next subject. Yeah, I think we are pretty much covered, except the volumes. There is number of changes in the volumes. Number of implementation is 8 now. Some of them are good for only small subset, but I decided to squeeze every % of the performance. I got another 3 implementations pending, so there will be unsafe. Unsafe will become part of the MapDB, core MapDB. There will be preprocessor, which will separate it from the Android and stuff, and sort of JVMs which cannot use it. So there will be some sort of flavors and stuff. I'll go through it a bit later or in separate video. And another change in the volumes is that it has much more methods. The thing is, for example, some sort of packing, long packing methods are part of the volume now, because for example if you have this code and you have like stuff like get unsigned integers and the underlying storage is, for example, byte array, you can take you can rewrite this method to work better with a byte array, and it will be much faster. So basically the volumes became a little bit smarter on their own, and yeah, that's it. The last thing I want to go through is the exception hierarchy in MapDB. The exception handling in MapDB 1 was a little bit weird. We have an IR error and some internal errors and assertions errors. Basically you couldn't be sure what exception will be thrown, if store fails, if it doesn't have enough memory, and so on. So I introduced exception hierarchy here, which basically there is single exception which will be always thrown in case of problem, and then it has number of subclasses, each corresponding to a certain type of problem. And the nice thing about this should give you some sort of hints what went wrong. So for example, there is out of memory exception, which is called when you fail to allocate enough memory, or when you don't have enough memory. There will be corresponding exception for the direct buffer and disk space and so on. But I would like to show you what happens if you try to allocate too much memory on the direct buffer and you don't have enough. So I will just run the unit test, and it will print well, it passed because the exception was thrown sort of as expected, but this is this piece I want to show you. So the original cause was Java lang out of memory direct by buffer exception, and maybe if you Google it you will get some sort of hints what actually wrong, but usually users will open new bug in MapDB, and it will be kind of hard to maintain it and so on. So I decided to add some hints to the exceptions themselves. So it says out of direct buffer memory, which is the same exception as the in here, but then it says what is the JVM settings, which will actually solve the issue. You simply need to adjust the limits on the direct memory, and if you allocate 10 gigabytes, it should probably work just fine. So that's it. There will be a number of changes like this in MapDB, and I will cover most use cases, and it should be much easier for the beginner who just starts using MapDB as drop-in replacement for Java collections to sort of iterate through the exceptions and common problems and stuff like that. For example, just to give you an idea, for example, if you have a hash map and you have a inconsistent hashing, it's a big problem for the MapDB because it can lead to data corruption. So I added some sort of code which will check for the inconsistent hashing, and if it detects inconsistent hashing, it will simply throw an exception and inform users that it needs to implement the hash correctly and stuff like that. Another thing is the logging. So for example, if you use incorrect settings, which actually works but is not optimal from the performance point of view, MapDB will just output warning in the log that you can improve by your performance, for example by using better serializer or this sort of stuff. Yeah, I think that's enough for now. Thank you if you stick with me for that 1.5 hour of these 2 videos, and thank you for being so keen about MapDB, and thank you for studying hopefully my code and stuff like that. So I guess that's all for now. Have a good day, and hopefully in 2 weeks MapDB Alpha 1 with some decent documentation and stuff like that will be out. That's all for now. Thank you.